Hello everyone. In this video, this is the problem that we will try and solve. Determine the normal force and acceleration on the 150 pounds skier the instant she arrives at the end of the jump, point A, where her velocity is 65 feet per second. And we are given with this figure. Solution. Okay, let's start. The question is the normal force and acceleration at point A. Now we are given that point A is located at the y-axis, okay? And we are given with this parabola equation. It's parabola because y is only 1 and x is squared. Now, so if point A is located at the y-axis and this is x squared, then this happens that at point A, the skier will be horizontal. Now it's no longer curving. So we can have point A here with our skier. Okay, it is now going horizontally for its acceleration along the tangential. So we said tangential is tangent at the curve, so it's going here, here, and eventually over there. Next is the normal. Since this is the center or the radius of the curve, then the normal would always be going in that direction. So at this point, it will now be vertically upward, the acceleration of the normal. Next, what about the forces? The question is, there's a normal force at point A. Therefore, our person has mass, so it will now be applied here, weight of the person. And the question is the normal force exerted by the platform to the skier. Okay. Using the equations of our Newton's second law applied in equations of motion, we have summation of forces along the normal axis is equal to the mass times the acceleration in the normal axis. Well, we have summation of forces along the tangential axis times the mass multiplied by acceleration of tangential axis. Let's try and solve first the tangential axis. Along the tangential axis, we have this one. This is also the normal axis. Along the tangential axis, there are no forces. Okay? Because we're only considered for point A. Because problem asks for point A. So we have 0 forces for tangential axis. Equals the mass of the skier is 150 times acceleration tangential. Simplifying, we'll be able to solve acceleration on tangential is 0. Next, for the normal. The forces along the normal, if we assume going up is positive, okay, going up is positive, we'd get the normal force minus the weight, okay, equals the mass of the person is 150. Now, the acceleration of the normal right now, we do not have, and we have that. Okay, so 150 AN, N, and W. The normal force is the question of the problem. We know that the normal acceleration is equal to v squared over the rho. Okay? We know that from our normal tangential components that the normal acceleration is v squared over rho. And rho can be solved is the radius of the curve, or if there is no radius, we have d squared over x squared. This would be 1 plus the first derivative. This is squared 3/2. Okay. Remember this equation in our normal tangential components. So we need the first and second derivative of the equation of the curve. So the first derivative, that becomes 2 over 200x, while the second derivative, we have 2 over 200. Okay. And we know that at the instant at point A, the value for the x is 0 because point A is located at the y-axis. That means it is at 0 value of x. So if x is 0, at x equals to 0, y prime becomes 0. While the second derivative, there's no value for x here, so it's still the same, that it's 2 over 200, or simply 1 over 100. Solving for rho now, I think we can just put it here. You have 1 plus the first derivative squared, which is 0, 3 halves, all over the second derivative. This is 1 over 100. Okay, so it will be 1 plus 0, so it becomes 1. 1 to the power of 3 halves is still 1. 1 divided by 1 over 100, this becomes rho is equal to 100, or 100 feet. Okay, 100 feet. So we now have here the normal force. What's the value? This is 150. The velocity is given as 65, so we have 65 squared all over 100. Now we also have the weight, okay, the weight of the person. So normal force is equal to 150 times 65 squared all over 100 minus, plus, the weight of the person is, you have it here 150, so this is 150, this is still mass, times 32.2 feet per second. Okay, gravity is 32.2 feet per second squared in the English system. So solving this, we have n is equal to 150 times 65 squared all over 100 plus 150 times 32.2. Okay, we have 150 times 65 squared over 100. Okay, 150 times 32. So we have 11167.5. Question is, what is the unit of this answer? Now we know that the unit of 150 is pounds. This is also pounds. The unit of 32.2 is feet per second squared. This is also, this now becomes feet squared, second squared due to the squared. This is over feet. Cancel 1 feet. This is now a unit of acceleration, so same as here. So our answer will have a unit of pound feet per second squared. Now we want a unit of only pounds for the normal force. Okay, not this unit. So what we do is we multiply it by 1 over 32.2, or simply the value of gravity again, so that we will be able to cancel out feet per second squared. Okay, we divide it by the value of gravity. So divided by 32.2, we have, okay, 346.8. 346.8 pounds. Right here, 346.8 pounds. This is now the answer for the normal force. The other question is the acceleration. We know that the acceleration squared is equal to the normal acceleration squared plus the tangential squared. We already have the normal acceleration is v squared is v squared over the rho quantity squared. The tangential acceleration is 0, so solved earlier, so this is 0 squared. So this is now removed, cancel the squared for both sides. So the A is simply equal to the normal acceleration. So we have 65 squared over 100, and this value is 65 squared divided by 100 equals 42.25. 42.25 feet per second squared. And this is now the acceleration. Okay?